Hello, this is Dr. Anand Rachagan, Associate Professor of Chemistry, Islamia College, Waniyambadi. I welcome you all to this lecture on infrared spectroscopy. In the past, we discussed about the UV visible spectroscopy and its applications in organic chemistry. From this class onwards, we shall discuss about the applications of infrared spectroscopy in organic chemistry. See, when compared to UV visible spectroscopy, infrared spectroscopy is giving you a lot of information about the structure of the organic molecule. The reason is you can notice a lot of absorption bands, which is because of the organic molecules in infrared spectroscopy. So, if you examine the infrared spectrum, then you can see a rich array of absorption bands. So, the good number of absorption bands provide a wealth of information about the structure of organic molecule in IR spectroscopy. See, this IR spectrum is a record of frequency against the percentage of absorption or intensity of absorption. The spectrum is actually a record of XY plot. In the x-axis, if you take the frequency, then in the y-axis, you have the percentage of absorbance or molar extinction coefficient, intensity of absorption. Frequency is the unit that is used for expressing the absorption of electromagnetic radiation in IR spectroscopy. That frequency is expressed in wave number. We all know that nu is equal to 1 by lambda. So if you divide the wavelength by 1 divided by wavelength, 1 by lambda, that is called as the wave number of waves per unit length. That is wave number. So, according to the wave number, the region from 4000 to 667 centimeter inwards is called as the infrared region. Wavelength is 2.5 to 15 microns. See, it is not in nanometers, microns. Higher unit when compared to nanometers, lambda. So 4000 to 667 centimeter inverse is your infrared region, and the region from 12,000 to 4,000 centimeter inverse is called as near infrared region. The region from 667 to 50 centimeter inverse is far infrared region. And the frequency of absorption expressed in wave number nu bar is given by the formula E is equal to Hc. So this is the unit for wavelength. Now let us try to understand the causes for the absorption of electromagnetic radiation in the infrared region. See, the organic molecule is made out of several atoms. We have molecules like carbon dioxide, linear molecules, where there is carbon and oxygen only, water, inorganic molecule, oxygen and hydrogen, methane, organic molecule, carbon, 4 hydrogen. So as we go further, we have more number of atoms in an organic molecule as the molecular size becomes bigger and bigger. As the molecular size and the number of atoms become higher, the number of chemical bonds which is connecting the atoms in a molecule also increases. We have more number of chemical bonds. So the chemical bonds which are made out of two electrons, it is just like our spring-like structure. Actually, the spring-like structure is in a constant state of vibration. Because of these vibrations called as molecular vibrations, which occurs at a particular frequency, the chemical bond is able to absorb electromagnetic radiation if it matches with the wavelength or frequency of the electromagnetic radiation. So let us try to understand how the molecular vibrations are taking place in an organic molecule by this video presentation. Let us go to a video presentation for understanding these molecular vibrations. Please listen to the video presentation. Through this video presentation, let us try to understand the molecular vibrations by comparing it with a ball, metal ball attached to a spring. Let us imagine that we have a fixed support. You have a steel ball. The steel ball is attached to this fixed support with the help of a spring. Now what I do is, if I pull the ball in this direction, then what happens? The steel ball will go out and it will come in. Steel ball will go out and it will come in. So this is your stretching vibration. The same steel ball, if it is attached to a fixed support with the help of a wire, if I push it down, it will go down and it will go up. So this is your bending vibrations. So the stretching and bending vibrations can be understood from this simple example. Let us consider a hydrogen molecule. We have a hydrogen atom connected with another hydrogen atom. There is only one sigma bond between the two hydrogen atoms. So the chemical bonds are just like our spring-like structures. If these are your hydrogen atoms and imagine that they are connected by a spring, this is the center point. This is the center point, or this is your just like your fixed support. So if you stretch the steel ball in this direction, it will undergo stretching. The same thing can be done in this direction also. So in both the directions, the steel ball attached by a common spring can stretch. If the stretching is uniform, then it is called as symmetrical stretching. So the steel balls both are going out and coming in, going out and coming in. Symmetrical stretching. The same steel balls, suppose if they are connected by a spring and this is the center point, suppose if the steel balls stretching in this way, when one is going in, another one is going out. When the other one is going in, the other one is going out. See? One is going in, another one is going out. Coming in, going out. Coming in, going out. So this is your asymmetric stretching symmetric stretching vibration. So, it is very clear that a simple molecule like hydrogen can show two types of vibration, stretching and stretching is of two types, symmetrical stretching and asymmetric stretching. Let us consider another molecule, namely water, H2O, where a hydrogen is connected with oxygen and another hydrogen is connected with oxygen. So this is your, see, these are all the spring-like structures. In such a situation, it can bend. Both can bend inside, both can bend outside. Okay, so the molecules through their bonds, they can show bending vibrations. So the bending vibration is of different types, and I will discuss all those things in the example given in the discussion, in the following discussion. Now let us continue our discussion about the bending vibrations. See, a molecule of water has two hydrogens, one oxygen. If all the hydrogens and oxygen remain in the same plane, and if the molecule undergoes a bending, it is called as in-plane bending. If the bending occurs within the plane, that is, the molecule or the chemical bond should not come out of the plane. You imagine the cell phone screen as a plane. The water molecule bends within the screen itself. It is not going up or going down. Such a bending vibration is called as in-plane bending. Suppose if the hydrogen atoms are coming above the plane or going below the plane, then that is called as out of plane bending vibration. Part of the molecule is coming out of the plane in which the molecule was originally present due to the bending vibration. So such a bending vibration is called as out of plane bending vibration. Now, coming to the in-plane bending vibration, see, just like the action of scissors, both the OH groups, OH bonds, they will come inside. Simultaneously, they will come inside. Such an action is called as scissoring. So, such a bending is called as scissoring in-plane bending vibration. Both of them bend in the same direction. Instead of bending in the opposite direction, with respect to each other, they are bending in the same direction. OH groups. So they bend in the left side first and then in the right side first. Right side, second. So such a vibration is called as a rocking vibration. So in-plane bending vibration is of two types. Just like the action of scissor, the OH groups are coming inside. They bend inside. That is called scissoring. And both the OH groups are moving in the same direction. They bend in the same direction. Such a vibration is called as a rocking vibration. And coming to the out of plane bending vibration. See, positive sign indicates that they are coming up. The OH groups are coming up. Both are coming up, coming above the plane in which the molecule is present. Minus sign indicates that the OH group is going below. So both of them may come up and go down the cell phone screen plane. So such a vibration is called as wagging. And if one goes up and another one goes down, and the other one goes down and the other one comes up, then such a vibration is called as a twisting vibration. So out of plane bending vibration is of two types. First one is wagging and another one is twisting. So in twisting vibration, it is just like our dance movement. One part is going up, on another part is going down. So basically, the bending vibrations called by another name, namely deformation, is of two types. In-plane bending and out-of-plane bending vibration. In-plane bending vibration is called as scissoring and rocking, is of two types, scissoring and rocking. And out-of-plane bending vibration is of two types, wagging and twisting. See, the organic molecule having good number of chemical bonds is showing an absorption because of these molecular vibrations. Let us see how these molecular vibrations are responsible for the absorption of electromagnetic radiation in the infrared region. See, I told you that the molecules may be linear or it may be non-linear. Suppose if a molecule is non-linear, then how many possible vibrations are there in an organic molecule? There is a formula for calculating the possible vibrations in an organic molecule if it is non-linear. The number of molecular vibrations is simply given by the formula 3n minus 6. So if your molecule is non-linear, then 3n minus 6 possible vibrations are observed in an organic molecule. And these possible vibrational modes are called as the fundamental vibrational modes. And they are responsible for the absorption of electromagnetic radiation in the infrared region. There is a condition. The vibrational modes which are showing a change in polarity, they only absorb the electromagnetic radiation in the infrared region. So basically, the absorption spectroscopy is of two types. One is infrared spectroscopy and another one is Raman spectroscopy. Infrared spectroscopy has good number of applications in organic chemistry, but Raman spectroscopy has very less number of applications in organic chemistry. That is why we study about the applications of infrared spectroscopy in organic chemistry. See, the organic molecule which is non-linear shows 3n minus 6 fundamental vibrations. If those vibrations produce a change in dipole moment, then such vibrations absorb electromagnetic radiations in the infrared region. See, the same rule is not applicable in Raman spectroscopy, it is just opposite. Those fundamental vibrations which are not showing a change in dipole moment due to molecular vibration, they will absorb the electromagnetic radiation and that leads to Raman spectroscopy. So often we used to compare the fundamental principles of IR spectroscopy with Raman spectroscopy, and we used to make a generalization that the vibration modes which are IR active are Raman inactive. The reason is the IR active modes, they produce a change in dipole moment. The IR inactive modes, they do not change in dipole moment and they will absorb electromagnetic radiation in Raman spectroscopy. So the vibrational modes which are IR active are Raman inactive. IR inactive modes are Raman active modes. So if your molecule has n number of atoms and if it is non-linear, then 3n minus 6 vibrational modes are possible. Out of the 3n minus 6 vibrational modes, only those modes which produce a change in dipole moment absorb electromagnetic radiation in the infrared region. Suppose if it is a linear molecule like carbon dioxide, then the molecule has the formulae, that is 3n minus 5 vibrational modes are possible for a linear molecule. And condition is the same. The vibrational modes which are showing a change in dipole moment will absorb electromagnetic radiation in the visible region. So if the molecule is non-linear, then 3n minus 6 vibrational modes are possible. If it is linear, then 3n minus 5 vibrational modes are possible. And the vibrational modes which are producing a change in dipole moment, they will absorb electromagnetic radiation in the infrared region. Now let us go to the next slide. See, in this slide, we have the formula giving you the frequency of absorption connected with some parameters. The frequency of absorption in IR spectroscopy, nu bar, expressed in wave number, is given by the formula 1 by 2 pi c square root of k pi mu. Nu bar is the frequency expressed in wave number, pi constant, c is the velocity of light, and in the square term we have k by mu. K is called as the force constant, which is a measure of the strength of the chemical bond which is connecting the atoms in the organic molecule. So if you are calculating the frequency of absorption of a particular chemical bond in an organic molecule, it is given by the formula nu bar is equal to 1 by 2 pi c square root of k pi mu. K is the force constant, which is actually a measure of the strength of the chemical bond. And mu is your reduced mass of the system. See, by a chemical bond, the two atoms are connected. The atoms, they have their own atomic masses. What is the reduced mass of the atoms which are connected by the chemical bond? That is given by the formula, that is given by mu. We can actually calculate. We have a formula for calculating the reduced mass of two systems if they are connected. Mu is given by the formula mx my divided by mx plus my. If x and y are the two atoms, then the reduced mass mu is given by the formula mu is equal to mx my multiplication divided by mx plus my. See, you have a section in organic spectroscopy and its applications, William Kemp. Go to William Kemp book. You can purchase it. It is available in the market. The cost of the book is around some 600 to 700 rupees. You can purchase it online also. So you can purchase it through Flipkart. We are spending so much of money in our everyday life. If you purchase one of the spectroscopic textbook, it will be an asset for you. Since you are completing MSc degree in spectroscopy, it is more useful in the preparation of examination, or at least till you are getting a job. So you can purchase a book. If you refer the Kemp book, then we have problems which is based on these formulae, nu bar is equal to 1 by 2 pi c square root of k by mu. So you will come across the formula for calculating the reduced mass. Mu is equal to mx my divided by mx plus my. See, First, let us see how reduced mass of the system is able to influence the frequency of absorption in infrared spectroscopy. Mu is the reduced mass of the system. I have given you various chemical bonds: carbon, hydrogen, carbon, oxygen, carbon, nitrogen, carbon, halogens. Carbon, hydrogen, oxygen, nitrogen. So the atomic mass varies. Sometimes the atomic mass can also be varied by changing to the isotope. Instead of hydrogen, you may have deuterium. So whether it is different atoms or isotopes of the same atom, whatever it may be, the mass differs. So automatically the reduced mass of the system varies. Mu is equal to mx my divided by mx plus my. So if there is a change in the mass of the atoms connected by the chemical bond, then what happens to the frequency of absorption? Since the reduced mass of the system is the denominator, the reduced mass of the system definitely influences the frequency of absorption, expressed in wave number nu bar. So, such an effect is called as a primary mass effect. So, what is meant by primary mass effect? It is mainly due to the change in the atomic mass or variation of the atomic mass of the atoms connected by the chemical bond over the frequency of absorption in IR spectroscopy. Sometimes the atoms attached to the chemical bonds, they also influence through their masses. For example, the first compound is your ketone and the second one is your acid chloride, CH3CO, CH3, acetone, CH3COCl, acetate chloride. If you calculate the frequency of absorption of the CO group, since the CO group is connected to a methyl group in the first molecule and chlorine in the second molecule, the frequency of absorption of the CO group varies. So, if the mass of the atoms attached to the groups for which the frequency of absorption is calculated varies, then also the frequency of absorption varies, and this is called as the secondary mass effect. So, to sum up, we must know what is meant by mass effect in IR spectroscopy, especially in determining the frequency of absorption. The frequency of absorption is calculated by the formula nu bar is equal to 1 by 2 pi c square root of k by mu. K is your force constant, mu is your reduced mass of the system, given by the formula mx my divided by mx plus my. X and y are the number of atoms connected by the chemical bonds. So the reduced mass of the system definitely plays an important role in determining the frequency of absorption. If the atomic mass varies, then it is called as primary mass effect. If the atoms attached to the group for which the frequency is calculated also varies, then that is called secondary mass effect. So the mass effect is of two types. One is primary mass effect, another one is secondary mass effect. Let us move to the next parameter, that is your force constant, K. I told you that the force constant K is a measure of the strength of the chemical bond. See, we have single bonds, carbon-hydrogen single bonds, carbon-carbon single bonds, they are sigma bonds. If you move further, carbon-carbon double bonds. Carbon-carbon double bonds. One is a sigma bond and another one is a pi bond. Carbon-carbon triple bonds. One sigma bond and two pi bonds. A double bond will be stronger than a single bond. A triple bond will be stronger than a double bond and a single bond. So definitely the strength of the chemical bonds plays an important role in determining or in calculating the frequency of absorption in IR spectroscopy. See, the strength of the chemical bond is influenced by various parameters. So, in the next lecture, we shall discuss about the various factors that are influencing the force constant, which is a measure of the strength of chemical bond and which determines the frequency of absorption in IR spectroscopy for various groups in organic chemistry. Thank you.